All right, let's see if we're all up and running here. Yes, stream health. Good. Hey, everybody. So, this is lesson 1G, rational expressions, an overview. So a rational is, it's like a cousin to the polynomials that we've been talking about so far. Lots of the polynomials, lots of the ideas and practices that we've put into place studying polynomials will apply when we're talking about rationals. So it's chapter 4.3 in the book. We're gonna actually take a running start to the content in this chapter, because there's a lot of things in rationals that have to do with what do you call those, fractions, and people aren't very good at fractions. So in today's lesson we're going to be relating a lot of things from fractions into a lot of things from rationals. I should note at the very start that there are two words. There are two words that aren't in the textbook that I'm importing from studying fractions. Those words are mixed and improper. Okay? So in this video we'll be talking about mixed and improper fractions. And then mixed and improper rational expressions. So let's get going. In this video, you'll be able to recognize what a rational expression is. So if somebody comes up to you on the street and says, hey, you want to buy a rational expression, and then shows it to you, you can say, yes, that is definitely a rational expression. I want you to be able to evaluate a rational expression. And by that we mean it's very similar to evaluating a polynomial expression. I want you to recognize the numerator and the denominator, two parts of a rational expression, and then I want you to be able to change a mixed rational into an improper one and to tell if a rational is mixed or improper. It's this is going to be a fairly light video, this particular one, and then we'll get into the heavier business in future parts of the lesson. So let's start. So in the past videos, we've talked about adding polynomials. We've talked about subtracting polynomials. We've even talked about multiplying polynomials. And so one question here is, can you divide polynomials? And the answer is yes. Yes, you can. So if somebody comes up to you with a polynomial, and then they say, hey, let's divide this by another polynomial, that's something you can do. It's not something we've talked about yet, because if you add two polynomials, you get another polynomial. If you subtract two polynomials, you get another polynomial. If you multiply two polynomials, you get another polynomial. But if you divide polynomials, you don't get another polynomial. Instead, you get a new type of thing. Before we go on, we don't write expressions like this when you're dividing polynomials. Instead, we adopt the notation that you use in fractions. You write it like this. Okay, so that line, that. Okay, so that's the notation. You recognize it from fractions, and essentially this means divide one polynomial by the other polynomial. This type of expression is called a rational expression. Where does the word rational come from? Rational is a word that gets used in a bunch of different contexts in math and other types of study. You can talk about rational arguments. In this case, though, the word rational comes from the root word ratio. Okay? It's a rational because it's a ratio. Ratio means you divide, right? So, you could talk about a ratio 2/3. That's a ratio. In this case, it's a rational expression because it's one polynomial divided by another polynomial. So, in terms of the basic operations, like evaluating them, they work just like polynomials do. So I'm going to write out some rational expressions for us to talk about. You can name a rational expression, and we're going to. You can name it using function notation, the way we have. So this one's the rational x. This one here is the rational, sorry, the first one's the rational f. This one's the rational g. Here's the rational h. So all these rationals are actually distinctive from one another. They have differences. So I'm going to introduce to you the way we distinguish between the different rationals. In polynomials, we talk about degrees, right? So this is a degree 1 polynomial, this is degree 2 polynomial. In rational expressions, we compare the degree of the numerator to the degree of the denominator. So this one, the top one has degree 1, the bottom one has degree 1. Okay? So they have the same degree. Maybe it won't let it, we're not dividing them. In the second one, the top has degree 1 and the bottom has degree 2. In this one, the denominator has higher degree than the numerator does. And that means something. In the last one, the degree of the top one is 3, and the degree of the bottom one is 1. And so in this one, the numerator has the higher degree. And just like in polynomials, where you can talk about the qualities of the polynomial based on the degree, in rational expressions, when you compare the degree of the numerator and the denominator, it means something. We're not going to talk about what it means exactly just yet, but just remember, you can evaluate, quick reminder, the one on the top, that's the numerator. And the one on the bottom, that's the denominator. Okay? So one thing we often find ourselves doing is comparing the degree of the numerator to the degree of the denominator. All right, that said, we evaluate rational expressions in exactly the same way as we evaluate polynomials. And by evaluate, I mean you choose a value for x, and then you plug it into the equation. So for instance, f of 3 can be calculated, g of 2 can be calculated, and h of 4 can be calculated. Let's talk about how to do that. So the first one, I'm just going to replace the values of x in this expression with the number 3. 3 divided by 2 minus 3. And then I evaluate. 3 over minus 1. Second one for g. 3 times 2 plus 4 divided by 2 all squared plus 1. So this becomes 6 plus 4 over 4 plus 1, which is equal to 10 over 5. And the last one, 4 cubed plus 1 over 4 times 4. So this is going to be 64 plus 1 over 16, which is going to be 65 over 16. Okay, so I want you to notice something about all these values. I'm not finished evaluating them necessarily. I can plug this into my calculator and get a decimal expansion. But I want you to note something about the results of evaluating rational. Often you get fractions. So before, sometimes we get a whole number out, and now you're getting something like a fraction. It's one number divided by another number. That's the type of operation rationals do. The result of these are often fractions. And so as a result, a lot of the ways rationals work, a lot of the ways rationals operate, a lot of the ways rationals are added together and subtracted and multiplied and that whole business simplified, they inherit a lot of characteristics from the math of fractions. So I thought we'd do a quick review of fractions. You need to notice something is that lots and lots and lots of people have trouble with fractions. And that means that you probably are a little bit unclear on some of the basics of fractions. So let's just review the basics of adding fractions. So classifying fractions. Alright, so let me write out some fractions for you. A fraction is just one number line another number, and the idea here is that it's overall a number, but it's overall represented by something that has that line is a shorthand for the line is a shorthand for what's it called, division. Okay, so fractions are numbers that can be represented as one number divided by another number. So for example, the number a half is represented as 1 divided by 2. The number a third is represented by 1 over 3, etc. Fractions are super useful when you're talking about cutting up quantities. You can say, okay, so I've got a pizza. I want to cut it into thirds. How do I represent that with numbers? Okay. So my point here is that often fractions are used to represent numbers that are smaller than 1. Okay? Not always, but there are some numbers that can be represented a fraction, or alternatively, you could represent it with a decimal expansion. So in this case, it's actually easier to represent the number as a fraction. So this number has an idea in it. It's a third. You take a pizza, you cut it into 3 pieces, right? That's easier to express as a fraction than a decimal expansion. I mean, the reason we haven't entirely gotten rid of fractions in this day and age where we all have calculators is that they've got some ideas built into them. And the ideas that are built around them are right on the face of things, which is to say, this is 1/3. You cut it into 3 pieces, right? So decimal expansions are often more practical in terms of computation, but fractions spell out exactly what's going on, and so they're useful. Okay, so we can classify fractions. So this is a number, and this is the same number. Okay, how do I know that the same numbers? Plug it into your calculator, and you get 1.25, 1.25. They're the same number, okay? That said, these are essentially 2 different ways of expressing the same number in terms of a fraction. This one is called the improper form. I don't know who called it that. It seems very rude. It's a very nice way to express that number. But this one's called improper. And this one is called the mixed form. Okay? Mixed numbers are numbers that you represent as a whole number plus one number divided by another number. Whoa. Whereas improper numbers are fractions where it's one number divided by another number. And it's all in one piece. Okay? So what's the big distinction here? How can you tell if you're looking at a mixed number or if you're looking at an improper number? Or rather, okay, so it's mixed if there's 2 things added together. Fine. How can you tell if a fraction is improper? The way to tell the fraction is improper is you're going to compare the top number to the bottom number. You're going to pair the numerator to the denominator. If the numerator is bigger than the denominator, then the thing is called improper. And the idea is any improper fraction can be represented as a mixed fraction. Okay? Does that all ring a bell? So for example, your grade 5 teacher might have been like, oh, 12 divided by 5. Well, that's a very nice fraction, but that's improper. Let's change it, and they'd ask you to change this and rewrite it in its mixed form, 2 plus 2 over 5. The implication being that it's easy to tell that this is a number that's, well, it's got a decimal expansion. It's easy to tell that it's a number that's bigger than 1, but it's difficult on face to tell how big the number is exactly. If you write a fraction in mixed form, you can tell that it's the number 2 plus a little bit, a number that's a little bit bigger. So it's between 2 and 3. Okay? So that was the idea from back when you were a kid. And we can represent fractions in these two ways. And so we have these two words. I'm going to use these words to describe rationals. The textbook doesn't, but I needed a way to distinguish between the different rationals we're talking about. So I'm going to inherit this, this nomenclature to talk about rationals. So I'm going to call some rationals improper and some mixed. Okay? So, long story short, if your fraction, the numerator, is a bigger number than the denominator, you can represent it as a mixed number. Why was that important? Sometimes it's useful for illustrating the numbers. It's not that important to me personally in terms of teaching it to you, but I want you to remember it, essentially. Okay, let's continue our fractional review, adding fractions. So somebody comes up and they tell you 1 over 3, and they tell you to add these. I have seen a ton of different ways that people do this wrong. There's just lots and lots and lots of different ways. So most of you have been taught the operational way to do this. By operational, I mean, what's the algebra? And you've learned that you can't add these together easily because their denominators don't match. The denominators don't match, so you're going to have a hard time adding them. It's easier to explain why this is tricky in terms of pizza. So you go over to your friend's house and you have a pizza party. And afterwards, so your buddies eat half of this pizza. So there's a half a pizza here. And then they eat this pizza down, so it's only got a third left. And then they're cleaning up for the night and they want to consolidate all the pizzas, so they put the same pizza in one box. So then it looks like this. You got a 1/2 over here and a 1/3 pizza here, which is fine. You could do that. You can put the two pizzas in a box. Everything's okay in terms of an operation. But the question here is, how do I describe this as a number? How much pizza do I have? And so the method for doing this is actually pretty fun. What you need to do is go back to your original pizzas. And when you're describing them, you need to cut them into smaller pieces. Okay? So you look at your final pizza and you go, you know what? I could cut this pizza into 6. And you'd have each of these is 1/6 of a pizza, and then you can count out the number of slices. So there's 5/6 of a pizza. What does that mean in terms of my original slices? It means that I would have to slice each of these original pizzas up into smaller groups, cut this one in 3, cut this one in half, so that each of these slices is the same size. And then once you've cut it up so that each slice is the same size, you can count them all up in the box. Does that make sense? In other words, we can't compare. Let me back it up. Back it up. Back it up. There's lots of little lines. Okay. So we're having trouble expressing how much pizza we have at the end because the slices in the box aren't the same size. And so we need to divide up our original slices, our 2 original pizzas, so that each slice in each box is the same size as the other one, as the ones in the other box. So in this case, that involves cutting this one into 3 and this one into 2, and now each of these slices are the same size. So when you combine them in this box, instead of having a half and a third, there are 3. So you'd call this one 3 6s, and this one 2 6s, and you'd be able to add. Okay? So long story short, adding fractions is actually pretty tricky on the face of it, because you have to rewrite these expressions so that the more smaller sized pieces of pizza. Okay? So how do we do that? It's actually a fairly fun operation. What we're going to do is we're going to multiply each pizza, each thing by a certain number, top and bottom, and we're going to multiply this one by top and bottom by a different number. The purpose being that we want, when we multiply these 2 numbers together, you want that to be the same as when you multiply these 2 numbers together. This is called a common denominator. There's a jabillion common denominators out there in this world. In this case, there's a fairly easy way to figure out what an easy common denominator, and that's just to take that number there, 3, and multiply this guy top and bottom by that number, and then take this number over here and multiply this one top and bottom by that same number. So this now represents the same quantity, but it becomes 3/6. And this one, those 2's divide away. So this one still represents the same quantity as before, only now you're rewriting this quantity as this. Now that the denominators match, you can add them together. But you're only allowed to add them together once the denominators match. So there's that intermediate step. And lots of people are actually really bad at remembering to do the intermediate step. And I encourage you not to be bad at that, because life is tricky. Okay. So we can turn a mixed fraction into an improper fraction fairly easily. So for instance, 1 plus 1/4. How do we turn this into an improper fraction? By that I mean I want another number with the same value where it's some number divided by 4. And this is probably going to be bigger, another number bigger than 4. How do I figure out what that numerator is? Well, there's a trick here. And that trick is to think about this guy here as a fraction. It's a fraction, the original number divided by 1. And now I'm adding 2 fractions, and so I need their denominators to match. 1/1 times 4/4, don't forget, 1/4 times 1/1, so this becomes 4/4 plus 1/4. Now their denominators match, 4 plus 1/4, so it's 5/4 in total. That's the trick. To review, what you have to do is you need to rewrite this original number, that whole number, you need to rewrite it as a fraction. Just divide it by 1, same value. And then you need to use the adding fractions trick. Boop, boop. This should all be reviewed to you, and if it is, that makes me really happy. So, how do we write an improper fraction as a mixed fraction? Do you remember how to do that? It was a procedure we call long division. I'm pretty sure the Egyptians knew how to use long division. People figured out long division a long time ago. And so here's the method for doing it. So let's say we wanted to write 1, 3, 4, 5 over 3. Now that is a terribly improper fraction. Look how big that numerator is. We want to write it as another number plus another number over 3, with the caveat we want this one to be smaller than 3. So it's got to be 2, 1, or 0. So how do we do it? I'm going to give you a short explanation. We're going to spend a longer lesson doing this, but let's just, I'll have you watch how I do long division here. You write that symbol, and then you write these numbers. You copy down the thing in the numerator, and then you're going to draw these little dotted lines. All right, and you're going to start filling in. Let's see. So I want to cancel out that number, and so there's nothing I can multiply by 3 to cancel that out, so it's going to be 0. So to cancel out this number, if I multiply 3 by, I need the largest multiple of 3 that's less than 19. I think if I multiply by 6, that's good. So 6 times 3 is 18. So now I'm going to subtract 18 from 19, and you get 1. I'll copy down the rest here. So what's the largest multiple of 3 that's smaller than 14? I think it's 12. So 4 times 3 is 12. I'm going to subtract those. 25. What's the largest multiple of 3 that's smaller than 25? It's 24, so it's times 8. 24 minus 1. This gives us it gives us two new numbers. It gives us this one and that one. This is called the quotient, and this is called the remainder. So the procedure goes 1945 over 3, that the quotient replaces that. 648 plus 1 over 3. And that's how long division works. And this should all be a review. I think I learned long division in grade 3. Sometimes when I ask first-year students about it, they can't remember how to do long division. It's a useful algorithm. If you take a math degree, you'll use long division a lot. Not because long division is particularly, like, we have calculators now. You don't need to divide two numbers anymore. But this particular algorithm is super useful. So if you know how to do it, it's great. You see it sometimes in Math 101 as well. So it's something that comes up. So we've just been talking about fractions. Just like there are mixed and improper fractions, there are mixed and improper rationals. Remember, a rational is one polynomial divided by another polynomial. Okay? So I'm going to write one example of each, and then I'll tell you how to figure out whether it's mixed or improper. Okay, so this one here is mixed, and this other one here is improper. Obviously, we're not comparing the numbers exactly. How about if I write that as 12? It's not the numbers specifically that we're comparing them when we sort them. I mean, this one's improper, but that 12 is bigger than 3 and 7. It's not those numbers. That's not the important part. The important part here is we're going to talk about the degree of the numerator and the degree of the denominator, just like I said before. In this one, the numerator, the degree of the numerator is 1, and the degree of the denominator is 2. If the degree of the numerator is less than the degree of the denominator, and then this type is added to a polynomial, then it's a mixed. I guess you call it a proper fraction, a polynomial plus a proper one. Anyway, long story short, the degree of the numerator here is 3 and the denominator is 2. And so if the degree of the denominator is smaller than the degree of the numerator, it's improper. So just like in fractions, when we can turn a mixed into an improper and an improper into a mixed, we can do the same thing with rational expressions. So for the rest of the video, we're going to focus on going from mixed to improper, because it involves a lot of the types of algebra that we've been doing up until now. So mixed, whoa, what did my line do there? Mixed to improper. Let's talk about how to do that. 3x plus 2 plus 4x x squared minus 1. The way to combine a mixed rational expression is really similar to the way we combine a mixed fraction. What was the first thing I had to do to make to add together this mixed fraction? I had to recognize the first term as its own fraction and multiply it top and bottom by the denominator on the second one. Okay? So just the same, I need to multiply this one. I have to imagine that it is its own rational expression and multiply it top and bottom by the denominator of this one. You might be asking why we're doing this. We're doing it this way because the output of a rational expression is essentially a fraction. And so the rational expressions inherit all of their algebraic properties and rules from fractions. Okay? So what was the next step in combining these two? The next step was I had to multiply these two numbers together, right? And so you got 28 over 7 plus 3 over 7. So my next step over here is I have to multiply these two terms together. Essentially, oh wait, hold on. In case you didn't know it, this one should be in parentheses. Usually when I write that step, the parentheses are implicit, which means that I don't write it, but I understand they're there. It's helpful to write the parentheses. So you'll see me in future steps writing those throwing in those parentheses. That's where they come from. I have to multiply that whole value by x squared. All right, so now I need to expand this. So it becomes 3x cubed plus 2x squared minus 3x minus 2 divided by x squared minus 1. Simplify the top, and now I can add them together. So now I would add these two together on the same numerator. Similarly here, this becomes 3x cubed plus 2x squared minus 3x minus 2 divided by x squared minus 1. And in the same numerator now, add them together. And now I combine them. 31 over 7. So now I just combine these. I simplify it. I'm essentially expanding it out. 2x squared plus x minus 2 . Okay, so that's the method. I'm going to do another example. We might do a few more examples. But the point here is that the method that we used to add together all of our fractions, go from a mixed fraction to an improper fraction, is literally the same method that we use to add together and combine an improper, a mixed rational into an improper rational. The idea here is that the denominators have to match. In order to add two rational expressions, the denominators need to match. Okay, let's try another example. For x squared minus 2x plus 3. I'm not going to write the whole fraction thing on the side anymore. That was just to elaborate on why we're doing what we're doing. To add these together, I need their denominators to match. So I'm going to say that the denominator of this first term is 1, and then multiply it top and bottom by x over 5, x plus 5. Okay. And now I expand this out. So this becomes 4x squared times x plus 5 minus 2x times x plus 5. Take your time expanding. Nothing's worse than getting a wrong answer because you rushed expanding a polynomial. And at this point in the game, if you're asking, what's the point of all these functions? We're talking a lot about operations. We haven't really explained what all these operations are for. It's true, we haven't. So right now I'm just focused on making sure that your operational rules are correct. We'll focus on some doing some applications in the next series of videos, but a lot of this is, like I said on the very first class, you only really get to see why we're putting you through all of these individual steps when you take your calculus class. What I'm building you is all of the steps and tricks that you will be using when you learn calculus. Alright, so I've simplified that numerator completely. Now I can combine them. And now I can finish simplifying them. So just be patient. focus on the skills I'm trying to teach you. If you can do them, then we're golden. Okay. So, at this stage in the game, you might be wondering, what was the point of all that? The idea, though, is that our original expression, which was 4x squared minus 2x plus 3, so this is an expression, 4x, did I get that right? 4x squared minus 2x plus 3. Yep. And all of the algebra I did suggests that 4x cubed plus 18x squared minus 7x plus 17 is the same rational expression. So one way to test this, and you might be interested in testing this to see if you did it right, is to just plug in a number. What number should we try? Let's try x equals 2. How about? I'm going to evaluate each of these at x equals 2 and then compare the values you get. So it's 4 times 2 squared minus 2 times 2 plus 3 plus 2 over 2 plus 5. So this is 16 minus 4 plus 3 plus 2 over 7. So that's 12. This is 15 plus 2 over 7. And my calculator, where'd my calculator go? Calculon, where are you? Oh, geez, what a time to lose your calculator. Ah, here you are. Okay, 15 plus 2 divided by 7. This is 15.285. Now let's try evaluating this one for the same value. The argument, if I did it correctly, it should always give the same value as this one did. 4 times 2 to the power 3 plus 18 times 2 squared minus 7 times 2 plus 17. 2 plus 5. Okay, so the first term is 4 times 2 times 2, 32 plus 18 times 4, 72 minus 14 plus 17, 32 plus 72 minus 14 plus 17. So 107 divided by 7, which gives us 15.285. Okay, you get the same number out as for each of these. For any particular number you put in, you get the same number out, and so they're the same. They're just two different algebraic ways of writing the same rational expression. Okay, well that's it for this particular lesson. Let's review. In a rational expression, it is an expression. There's two parts. You got your numerator and your denominator. The numerator and denominator both have degrees. And when we compare those two, we can tell whether or not the expression is improper. Improper means that the denominator has a lower degree than the numerator. Anytime you see an improper rational expression, it means that you can write it as a mixed expression. Okay, and there's a relationship in basic arithmetic that has to do with whole numbers, where if you add together or subtract whole numbers from each other, you get another whole number. And if you divide a whole number, if you multiply a whole number by another whole number, you get another whole number. Contrast that to fractions. Fractions are different than whole numbers because they're whole numbers that are divided into smaller pieces. And so fractions have a lot of similar properties to whole numbers, but they have additional properties on their own. And this is interesting because whole numbers, they work a lot like polynomials. Or rather, polynomials work a lot like whole numbers. Often the value of a polynomial, when you put in a number, you'll get out a whole number. So if you input a whole number to a polynomial, often you will get a whole number out. It's not always the case. Polynomials are a pretty diverse bunch. In this class, you'll usually get a whole number out. If you add two polynomials together, you get another polynomial. If you multiply two polynomials, you get another polynomial. On the other hand, rational expressions are when you divide one polynomial by another polynomial. And so rational expressions have the same relationship to fractions as polynomials do to whole numbers. They're related. So if you've mastered the algebraic properties, the algebraic rules of fractions, it's a good first step to understanding the properties of the algebraic properties of rational. Okay, well, that's it for now. We've got a lot more to talk about in the future, but that is it for now. Thank you.